Today I wanted to talk about the slider crank mechanism. In the previous chapter, we modeled the crankshaft. Now we take the output of that model and feed it into the slider crank model to calculate the position of the piston. Simply, we want such a model that theta, which is the crankshaft angle, is the input, and y, which is the piston position, is the output. First, we place the coordinate system. I choose the origin as the center of rotation of the crankshaft and the vertical axis as a starting angle. Define the y and theta. We will try to calculate the value of y for theta ranging from 0 to 2 pi. I want to add the offset value e found in many internal combustion engines to make the calculations more realistic. Now let's stop the system at a random position and simplify the parts. I defined the distance from the top of the piston to its pin as h. Because h is constant value, we will compute the y minus h. While calculating such mechanisms, it's good to think of them as a polygon. Furthermore, we can scale the polygon in any direction and calculations will not change. I'm stretching the shape to expand the workspace. We define the crank throw as L1, which is also defined as half of the stroke, and rod length as L2. On the angle axis, we said that theta is the crankshaft angle. In addition, let's define the beta and gamma angles as shown in the figure to use them in force calculations later. We know that the sum of the interior angles of tetragon is 2 pi. So we can define our first equation as theta plus beta plus gamma equals pi. There are multiple methods of finding the relationship between angles and lengths. I like right triangles, so I will try to create one. Let's take the cosine of L1 and redefine the right side. After that, take the sine of the L1 and add the e to complete the right triangle. We can simply calculate the gamma angle with trigonometry. And you notice that I use the absolute value because arcsine is defined in the range of -1 to +1. Lastly, we write the relation of the h's with the help of the Pythagorean theorem. Since the value we are looking for is y, we leave y minus h minus L1 times cosine theta alone and take its square root. We draw all terms except y to the other side. And here we have it, a theta-dependent function of piston position, while the L1, L2, and E as so. That's the sum of whole story. We can visualize that equation by writing it Python as so. To make it pretty, I add a grid representing each centimeter. Choose some values for L1, L2, E, and h, and calculate the equation from 0 to 2 pi. Because the equation is parametric, we can change the, let's say, E, and see the change in motion from the graph. We can change the length and that's tell us another story as seen in the graph. You get the point. Remember I mentioned that we will use beta and gamma angles when doing force calculations. As seen in the animation, the force acting on the top of the piston flows through connecting rod and makes a torque at the crankshaft. Although this equation will be useful for the piston explosion and compression process, it's useful to calculate it now. While carrying the force vector, we multiply by cosine gamma, multiply by sine p minus beta, and multiply it by the torque arm L1. Now any force acting on the top of the piston can be added to crankshaft torque or vice versa. Let's test whether the equations we calculated are correct in the Matlab simulating environment. The input block with a slope of 1 represents the angle of the crankshaft. In the Matlab function, theta is the input and y is the output as planned. Also, force on the top of the piston can be converted to torque on the crankshaft. And the equations are same as we calculated. After running the simulation, we can see that the piston position is as it's supposed to be. Just to get rough idea of force and torque relation, we can set the force as let's say 3 and run the simulation to see the results. we can see that the torque value behaves quite differently according to the position of the piston. And it's negative while the connecting rod is on the other side. The values seem quite logical. On the C# side, we define a piston class that contains position, force, torque, and height, which is h, as a variable. The kinematics function takes the necessary dimensions and calculates piston position and torque effect on the crankshaft at specified theta angle. In the Unity scene, I add a piston, rod, and crankshaft section, create C# file, name it piston, code parameters, and code the function we discussed, the equations, inputs, and torque equation. The crankshaft model is the same as we computed in the previous chapter. If you haven't watched it yet, you can find it in the internal combustion engine model playlist. I define the game objects, simulation variables, and parameters in the discrete model C# file. Create crankshaft and piston class, set and start the timer. In the game, whenever I press the keypad 0K, constant 10 Nm torque is applied to the crankshaft. In the discrete loop, necessary functions are called. Lastly, the crankshaft game object angle is updated with the calculated angle. The piston game object position is updated with the calculated position, and connecting rod position and rotation are simply calculated with respect to the piston position and crankshaft angle with that function. Finally, we can run the simulation and enjoy the model. As you can see, I'm pressing and releasing the torque input K, and the system works perfectly. Even more exciting when we think that the model is running in 10 kHz. In the next chapter, we will add the camshaft and valve system models to the simulation. Stay tuned.